Are there any questions? I don't know if anybody's had a chance to try out any of the homework from the stuff we've done recently. Okay, maybe not. Understand. And real quick, here's one little thing. Something that math teachers are trying to be better about is, for example, I already told you my story about when I was taking math courses and I had 3 jobs and blah, blah, blah. So the teachers that had homework that was due every day, my homework grade went to shit because I could not do I physically could not do homework every day. So some of my colleagues are a little stuck in the past in terms of setting up rules so that you're not making students feel like there's no hope for them because of stuff out of their control. Does that make sense? So some of my colleagues feel that that's like coddling or whatever. And I'm like, no, it's just being realistic. You want them to have a reason to do stuff. You have to kind of meet them where they are. You can still have hard deadlines and so forth, but don't make it every day. That's why my deadlines are the way they are, right? I figure between the time I say something and the test time, you should be able to find time to do it. I'm not going to make something due tomorrow because who the hell knows what's going on in your life today? Maybe right after class you got something you got to go to. Who the hell knows? Anyway, and you're gonna, who knows how old your people are gonna be, and some of them are gonna have family responsibilities. They gotta get home and they gotta watch the kid or whatever, right? That their little brother, they have to watch them and whatever. You never know. So you want to be a little bit, build that in. Anyway, that's all side note. So I think last time we had just gotten into subtraction, if I remember correctly.
Yeah. Tapped on the takeaway method.
I'm gonna do a little bit of lecture and then we're gonna watch some of these kids again, work some problems out. I have a feeling you guys are cool with that, because they're cute, and also I'll shut up for a little bit, so that's always nice. That's a twofer. What is the one method we talked about so far with subtraction? Takeaway method. So there was the set model, and this works for addition, subtraction. It's also going to work for multiplication, division. And then there's also, what was the other one?
There was set model. There was
Measurement model. Yeah. And normally the measurement model kind of means number line, but it doesn't have to. We'll see today with multiplication and so forth what else it could mean. So far we've talked about those. Those are true for addition, subtraction, multiplication, whatever. We're gonna have these main kind of models. Oh no, do you work? Sort of. The only one that's really working well. Shite. So then we have the takeaway method. What would that look like? Can you make a takeaway out of 5 minus 2 set model? Good. Oh wait. Make a set model illustrating 5 minus 2. If you're not sure, you can draw a dumper, just so it looks like no. Try something. So how much do I start with? 5. So you can make your favorite whatever. I just make dots. You can make whatever shape you want to. And then takeaway literally means take it away. So like I can do in little dotted, I can pull those out. Looks like somebody's screaming into the void. So, and of course 3 is left. So this equals 3 because that's how much is left when I take away 2. Okay. So one level of course it is, but again we're talking about little tiny people who don't know our number system. So this is kind of nice. They can latch onto this. You can have an actual physical grouping of things, and they can actually take 2 of them away. They can count what's left, and that kind of builds this idea of what subtraction is. What about measurement model? How would you show this in a measurement model? Number line, right? With a set model, I drew a picture that started with 5. So measurement model, I want to draw a picture that starts with 5. Do my number line. Yeah. 1, 2, 3, 4, 5. So I start with 5. Bam. visually what I do. What do I do to show minus 2?
Kind of go backwards.
Go backwards,
like
yeah.
to the bottom.
So if I go back 2, I end up at 3. Sweet. So there's another way to illustrate that 5 minus 2 is 3. I like it. Now, here's something interesting. You're going to see this a lot. You're going to hear this from me a lot. When you're teaching a new concept, you try to build it off of something they've already worked with, right? Every math course I try to do that. Most math courses build, which is why missing math class sucks, because you're not going to understand with the next lecture, because it's going to build on the one before, right? Oh shoot, I'm kind of stuck with colors. No, I've gone and lost my train of thought. Oh yeah, okay. What is the, so right before I would teach subtraction, I obviously would have taught crazy. Is there a way to think of subtraction that actually relates to addition problems?
Adding negatives.
No, negatives don't exist
Oh, yes.
for us yet. So if I said, what is 5 minus 2, the answer must be the number that when I add 2 to it, I get 5. You with me? When I say 5 minus 2, the answer has to be the number that if I add 2 to it, I get 5. This is called the missing addend approach. Yes?
How do you know it's 2? Is it because that's the number that's being minus 2?
That's the problem. That's the problem I'm talking about. So 5 minus 2 equals something. That implies that 2 plus something equals 5. Is that cool? Again, this is sort of like, oh, well, yeah, but again. And this is beautiful because students will have started to learn and memorize some addition facts. So this becomes not a brand new problem, but like, just tell me what number would go there, right? And they know this. They memorize some of the addition stuff. So they're like, 2 plus 3 is 5. So again, it's this idea of feeling like you have something to connect to build on top of. Now, there's not much more to be said about that, to be honest, is exactly what it sounds like. So if I want to make this a little more formal, A minus B equals C. Let me see if you guys, if and only if A equals B plus C. What if and only if means is it works both ways. If this is true, then that's true. Is that cool? If this is true, that must be true, right? And if this is true, that must be true. So if I say if and only if, that just means it works both ways. You guys with me? Okay. You guys really with me?
There's too many F's in that if, and it's making me mad.
If and only if. So we, math people, we don't like to write too much. Me, because I really can't write too well. So what we have at the moment is something we can create called a 4-fact family. If you don't have enough F's in your life, here's some more. Four fact families. So what the shit is that, Jeff? Well, if I start with like 8 minus 5 is 3. Can you write another subtraction problem that captures this idea that uses the same numbers? If 8 minus 5 is 3, what's 8 minus 3? 5. Now can you write an addition problem that uses the numbers that captures the idea?
5 plus 3 is
5 plus 3 is 8, and what's another addition problem that is 3 plus 5? Yeah. 4-fact family, right? If any one of these is true, then the other 3 are true. Yes, am I with me? Okay. So just a little side note from like algebra, for example. If I had this, and I had to solve for y, the quick way to do that is to say, okay, if 7 minus one piece is the other piece, then 7 minus this piece is that first piece. Right? That's part of a 4-fact family. I don't have to subtract 7 and divide by -1. I could just freaking switch those two. Why does that work? Of course it works. 8 minus 1 chunk is the other chunk. 8 minus that chunk is the first chunk. If I subtract 1 chunk, I get the other chunk. Does that make any sense? You guys cool with the word chunk there? 8 minus 1 piece of 8 is the rest of 8. So 8 minus that piece of 8 is that first piece of 8. It just switches. Okay.
Everything is interchangeable.
So again?
It's like everything interchangeable.
Yeah, so interchangeable around, and you can also change the operations. You just gotta be careful. So if any one of these statements is true, they're all true. Yeah, okay. So that's what we call a family. Yeah. Okay. So let me see. I want to get to a point where I can play some videos. Yeah. So let me ask you this. Amongst all the strategies we've talked about, which strategy does this word problem, not a horrible word problem, all right, you'll see. I had 8 trucks. Toy trucks, right? I'm a little kid, yes. I had 8 trucks. I gave 2 to, what do they call it? Billy, sure. Hey, Billy. I gave 2 to Billy. How many do I have left? My question is not what's the answer, because, my question is which strategy does that relate to? So what strategies do we have? We really just have take away, missing addend, right? You guys with me? Yeah, so take away. This is very obviously take away. He had 8, took 2 of them, gave them away. So that's take away. So we figure out how to, and the answer of course is 6. How could I have another problem where it's actually missing addend? This is more interesting. Yeah.
I had 8 trucks, now I only have 6. How many did I give to Billy?
Okay, alright. I had 8 trucks. I now have 6.
Came with a bit of better example.
How many did I give away? Did I give to Billy? Trying to pay Billy off. He's my bookie.
He's the loan shark.
A little bookie. Do you guys see that? That's like missing addend in a way. There's a way to make it more directly missing addend. Yeah. No?
Would that not be like set model though? Because
Oh, in terms of what kind of setup I could do to solve them, I could do either.
we could do anything. I mean,
Yeah.
it's a simple problem. But.
Yeah. But I mean, they don't necessarily require set versus measurement to be done. Yeah. The question is it takeaway or is it missing addend? Right. So here's a really direct missing addend. I have 2 trucks. Billy's got 8. How many more do I need so I have the same as Billy? Do you guys understand? That is very directly missing addend because in that case, physically, I am missing something to have the same as him. You guys kind of with me? That is also kind of a new thing. That is what's called, and this is going to be really obvious, this is called comparison. I'm comparing myself. I'm comparing myself with Billy. Does that make sense? So there's a whole idea of comparison problems. Okay. You could also say, let's say my house is 8 miles from Billy's house. Right? My parents are letting me walk 8 miles, but oh well, I'm not doing. I walk 2 miles. How much further do I have to walk? You see how that's missing addend? What am I missing from 2 to make it 8 total, right? Do you guys see that? Okay. Yes.
Could you write it as like kind of a different problem? It would be the same thing with like my house is 8 miles from Billy's. I walked halfway. How far did I walk?
Oh, that's bringing in division and so forth.
Okay.
We're not ready for that. Yeah, that's too advanced.
So instead of
Yeah, that could be an example problem I give you, exactly. So you identify what strategy is used in each case, and then it could ask you, rewrite that so that it becomes the other strategy, right? That could be a question to ask you. Are you guys semi with me? Okay. That's not too bad. So most of us, when we say subtraction, most people think of takeaway immediately, because that's what we think of when I had so much and they took this much, right? For example, April 15th is coming, you know. But the other thing, the missing addend, is actually the way that we normally learn it first, because like I said, you will have just learned addition. You want to have a kind of a connection with the next idea. Okay, maybe. Let me see. Blah, 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 blah. Okay, good. That's a perfect place to stop for a moment. I am going to pull up the videos, which, as the great teacher I am, I did not get ready before class. Learn from what I don't do. While that's warming up, anybody else not get their test back?
Okay, don't forget to turn off the camera.
Oh yeah, thank you. Anybody else not get their test back? Okay.
Did you bring the homework back on?
Don't forget.
To stop the recording, and I got YouTube took my video down. Copyright, yeah.
A video like
I'm a bad
like
boy.
12 views.
Yeah. If I get 12, that's pretty good. Okay, so we've talked about addition, we've talked about subtraction. Not surprisingly, we're going to talk about multiplication and division now. And this is one of the most common, no pun intended, this is one of the most common core complaints, a lot of C's, is related to what we're going to do today. So with multiplication, what is multiplication based on? As I'm writing them, like, am I spelling them? Okay. What is it based on? It's based on addition. Again, it inherently has a tie to something they would have done before. It's just a quick way to add, right? If you think about it that way. So if I had to do 5 plus 5 plus 5 plus 5, what's the shortcut?
5 times 4.
Yeah, this would actually be 4 times 5, because there's 4 5s. This is what confuses the hell out of parents, for example. And I don't blame them, because again, they might have done this very same thing way back when, and they forgot, because they know what multiplication is now. 4 times 5 means 4 of these, 4 5s. So what would 5 times 4 mean? How would I rewrite that?
5 fours.
Yeah, 4 plus 4 plus 4 plus 4 plus 4. Yeah. Now very quickly, that is one way to prove to a student what property works for multiplication. What property works. Those two are the same, correct? 5 plus 5 plus 5 implies it's the same thing as 4 plus 4 plus 4 plus 4.
The commutative.
That is the what property?
Commutative.
Commutative. When I move individual numbers, that is commutative. Let me stop for a minute. Yes?
At what grade would you start introducing this?
Oh, good. Just to remind you guys, because I am really bad about this. I don't know if you know this, but have I told you I've never taught elementary school? So part of me always feels like a bit of a fraud. Yeah, exactly. Right? You ever heard of imposter syndrome?
Yeah.
So part of me is up here going, I'm teaching you, I'm not here to teach you how to be an elementary, I'm not, even though every now and then I'm talking about just teaching in general. I'm never going to try to teach you how to be an elementary because I've never done it. I have tutored elementary students. I used to do it all the time. I used to volunteer and tutor. There's this Newtown Elementary, and they had the Roadrunners was their mascot. Anyway. But I've never taught elementary school. So I am very focused on the mathematical concepts to tell you. I sometimes forget, for example, and just to remind you guys, in the beginning of every chapter, it gets to the right place.
This is what each grade should be able to do.
Yeah. Perfect. So like I can't speak from experience. If you ask me when is this done, I actually have to go reference something like this. Now if you talk to an elementary teacher, they're gonna know when things are taught, because more than likely they've taught a lot of the grades over their years. Oh, you don't wanna zoom in? There you go. So right at the beginning of section 3.2, which is where we are now, right here, Common Core grade 3, and then it tells you the idea from Common Core that you're supposed to hit. You guys with me? And it even talks about, sometimes they'll have, for some reason they don't have this here, but they'll have, for example, yeah, here, this is perfect. NCTM. And they have in the very beginning of the chapters, they actually have general ideas that you're going to discuss in the entire chapter from both Common Core, NCTM, Standards for School. There's a lot, I don't know if you guys know, I'm not even sure which class you go into that discusses this in your elementary education program. But at some point they're going to talk about all the different, there's not just Common Core, there's all these different things that you kind of have to address and you have to kind of keep in step with. So that's going to be exciting. As a college professor, I ain't got nothing. It's fantastic. I'm sorry, I got a little bit. I have what's known as the course outline of record, so it lists all the stuff we're supposed to kind of like teach. Are you guys kind of with me? But beyond that, I have no like external thing that tells me you must do this. And that, you guys kind of with me? So it's nice. Sorry. I am very jealous of you guys though, because I'd love to teach a student something for the very first time. Most of my job, I'm teaching somebody for the 5th time. You know what I'm saying? Yeah, they've already done factoring many times, and here I am. We're gonna factor today. Oh God.
Could go back to elementary school.
Okay, but I'm sorry. That was a good question. So it looks like grade 3, roughly. Whoever asked the question.
Okay. My daughter's in 2nd grade, so I was trying to, they're decomposing numbers now. So
What do you mean, like having like 10 and then breaking it up into 5 plus 5?
There's a whole bunch of bubbles and stuff.
Okay,
and,
okay.
Numbers. So I was wondering, and then I tried to explain multiplication, and it was not. I didn't.
What I would love is if you felt comfortable doing this, because I do have some of these, but if you wanted to bring in, like if you could take a copy of a worksheet, that would be cool.
And have her do it.
No. Have us look at it.
Oh yeah.
Like an example worksheet, yeah.
Absolutely.
Because I have some that are like generic, but it'd be awesome to get some that are like from an actual.
Yes.
Yeah. Okay. All right.
An industry expert.
Multiplication is repeated addition. Is really what it is, right? And that's why when you see like 4 in front of something in algebra, that really can be broken down as x plus x plus x plus x. Okay. All right. Now I'm kind of off track. Where am I? Okay. So again, we could do the same thing we were doing before. We could do set model. We could do measurement model, right? So here's the basic idea. If I see A times B, and yes, we will still use the x, because you're going to be using the x. And once you get to a certain point, you realize x means unknown, so we don't want to use it too often. A times B would mean A B's. So I'd have B plus B plus B, and I'd have A of them. A add-ins. Okay, got it with me? Same way we do 4 times 5 is 4 5s adding, 5 times 4 is 5 4s adding, blah, blah, blah. Okay. So you got the repeated addition approach to multiplication, and you want to quickly get away from that, because then if you're going to do 80 times 3, do you want to write 3 80 times? No. How would I represent 4 times 5 using a set model? Remember, remind me, this is something really important for us. And by the way, do you understand if an elementary teacher gave a student this and said, write this as addition, and they gave that answer, do you see that that would be wrong? And this actually ties in to the concrete way we think of addition. They're both different things. The fact that they are equal to each other.
I think it's the same exact thing we're talking about now too.
Oh, cool. Oh yeah. All right.
I didn't know if he was gonna use that.
Let's see. I like that. Yeah. If either you could like bring copies in, or
I could email it to you right now.
Email it to me. Yeah.
Waller.
Well, Jeff.Waller@gcccd. Okay. So the first number tells me how many of the second numbers, right? So how would I use a set model? Yeah, exactly. So I got 1, 2, 3, 4, 5. That's 1 times 5.
Yes.
So now I got. Okay. And then a student could just count all the dots and see that it's 20. Yeah. Now, real quick, what would the difference be with 5 times 4? Yeah, I'd have 1, 2, 3, 4, and I'd have 5 of those. Yeah, okay. I like it. Yes.
How would you explain to a younger, I know you just said you don't have direct experience, but how would you explain to a child the difference between, because you know how it's commutative, it works either way, how would you explain
Well,
to them
Here's the thing.
that they're different?
Do you think a student could grasp this pretty quickly? 4 times 5 means you have, here's one group of 5, now make 4 of them, right? And then they can count the dots to see what the answer is. You can kind of see leading a student down that path. Then he could do 5 times 4, which to the student would be a different problem, yes? Especially when you're talking about stuff they can hold and move around. That is a different problem. I want 5 groups of 4, right? And then from the fact that you always get the same answer both ways, you develop the commutative property. You don't tell a student the commutative property is a thing. You let them see it is, right? It's just a thing that emerges.
Yeah, but like, let's say that they notice that they're the same answer, and then they ask why one would be wrong compared to the other one, if it's the same answer.
Oh, from their perspective, they're not going to even. They will be told that the first number is how many, and the second, how many of these groups, right? They will know that. So a student could get that confused, sure, but it's because we have to kind of have, how do I say this, a way to interpret it concretely that is always the same. Or else I'm being told people can interpret it a lot of different ways. So we want it to mean the same thing. So it's always going to mean this many of this groups of this, right? This many groups of this size. Are you with me? So I got 4 groups of 5 or 5 groups of 4. And again, the reason we're not making those two different, we're understanding that they are different. I got groups of 5. So when we're working with manipulatives that they can touch and move, this will be very concrete. That will be a concrete different thing. But then we can say mathematically, they're the same. So we don't just say, hey, commutative property is a thing, and here's what it means. No, we say, hey, look, that seems to always be true. Maybe that's always true, right? And then later you can start to prove it once they learn some more stuff. In fact, a little bit of what we're about to do. You guys semi with me. Now, here's one place where measurement model will eventually look a little bit different. And so will set model. But right now, what would the measurement model look like for 4 times 5? So again,
Like just 4 long lines?
4 times 5.
Then 4 or 5 long lines.
Yeah. So I go 5, 10. So I got 1 5 long, 1 more. 1 more, and then I go, I ended up at 20. Okay, right? 4 groups of 5, again. Now, there's another method that I sometimes call the ice cube tray method, but it's the rectangular array method. And this is where it gets a little bit murkier. Oh, that was me, I'm sorry. Sorry. The physics teacher and me just got excited. Conservation momentum and all. So the book calls it the rectangular array method. And to be honest, that's what it is. It's not just what the book calls it. And under this, you can use set model or you can use measurement model, and they sort of look very similar. So 4 times 5, I could have 4 rows, 5 columns, right? So normally, one way you can look at multiplication is just finding the area, right? So if you want to do 4 times 5, you make a triangle that's 4 by 5. So the area would be 20, so 4 times 5 is 20. But this is kind of nice because again, you can count them, right? So this is the set model for a rectangular array. And the measurement model looks very, very similar. And this really is the ice cube tray approach. You just would have, what was it, 4 by 5, right? It's got to be 4 rows. The first number is the number of rows. The second number is the number of columns. And then again, the student can sit there and count them all and see that there is 20. Are you guys?
We're gonna be using this item class and stuff.
Hell yeah.
And that one is the rectangular.
Yes. Rectangular array method. Rectangular array. And you got the set model and you got the measurement model. And they're basically the same thing, aren't they? Like this just uses rectangles and this uses circles. Ooh. You could use triangles, any shape you want to here. You guys kind of, just like you can for any set.
Wow, how would you use a triangle for that?
Oh, I mean, just instead of circles, use triangles.
Oh,
Yeah.
okay.
My, not like a rectangular array.
Okay.
Oh my god, no.
Could.
That would be neat. Because everybody, and again, nothing too groundbreaking, but when we're gonna get somewhere nifty is when we're multiplying 3 numbers together. And what would that mean visually? Oh yeah. So we're not quite there yet.
Is that gonna be in this unit? This
Yeah, it's
section?
gonna be today, we're gonna do it today.
Fun.
I know. By the way, yeah, this week has been insane. So today is a bunch of me lecturing, just because that's the way it's going to be. Next week I got some worksheet stuff that we can catch up on the stuff we've done since the last test, and you guys can try it out. I'm going to pull out some manipulatives. Yeah. Yeah. Does anyone remember what this thing is?
It's the thing that you do, where they
Yeah.
add it to each other.
So if A was 1, 2, and B was X, Y, Z,
You would multiply that.
what is A cross B? No.
One X.
Yes, good. So remember, the Cartesian product is making all of the points you can make, right? 1x, 1y. There's a lot of weird comments. 1z, 2x, 2y, 2z, right? So how do I connect that with numbers? If I call little a the number that's in set A, and I call little b the number that's in set B, you guys all with me so far? You guys remember this notation, right? What is little a then for this problem? What's the value of the a? It's 2. Little b is 3. Right? Then a times b, let me not do that because Cartesian. A times b will equal the number in a product B, a Cartesian product B. And sure enough, what's 2 times 3? Holy shit. And how many things are in A cross with B? 6, yeah. Now, a nice visual to really get at what this is saying is called a tree diagram. Has anybody ever heard of a tree diagram?
That's what goes like starts in the bottom and then just spreads out.
Let me show you. When you were making those points, what were the options for the first piece of any point? The first piece of any point, what were the options?
1 or 2.
1 or 2. So here's what a tree diagram looks like. I could choose 1 or I could choose 2. I don't know if you ever read any of those Choose Your Own Adventure books.
Oh yeah, that's what
Oh my god, I read those like crazy when I was little. I always would choose the one where it's like I turned and it said, and I'm like, damn it, I died. Shit. So the first choice is 1 or 2. No matter which one of those I choose, how many choices do I have for the next piece?
3.
3. X, Y, or Z. Are you guys with me? So this is why you can see why we call it a tree diagram. This would be X, Y, Z. X, Y, Z. So this would be 1 X, 1 Y, 1 Z. You guys see? How many do I end up with? 6. Yeah, yeah. So there's actually a way to construct the points too. Right? You just read off 1 X, 1 Y, 1 Z. Okay. If you do any probability classes, tree diagrams can come up. They can model choices we have to make, and then we can determine probabilities of things.
Computer science classes too.
Huh?
Computer science classes too.
Computer science? Hell yeah. Whoops, sorry. All right, how you guys feeling so far? I mean, so we're talking about different ways to look at these things, different visual representations of these things. You might have an issue with why is 4 times 5 concretely different from 5 times 4. I need to make sure you understand, of course it is. They end up equaling the same number. Yay. So that's where we learn commutative property. Concretely, they represent 2 different ideas. They happen to equal each other. Somebody remind me, what is the associative property? Here's where I'm going to challenge your artistic ability.
The 4 plus 2 in parentheses, then adding a 3 is the same as the 4 plus a 2 and a 3.
Yeah, so if I've got, let's say, let's make some nice small numbers.
If
2 times 3 times 4 versus 2 times 3 times 4. Now we all know both of those are the same, whatever the hell you are. Whatever. How would I show them? Help me out. Let's start here. How would you show 2 times 3 with the rectangular array method? 2 times 3. Can you just draw it real quick for me? 2 times 3. Rectangular array method. Measurement model, so the blocks, right? I call it the ice cube tray. You can call it whatever you think I should have called it. All right, so now it'd be up. What would it be?
2 rows.
2 rows.
2 columns, 3 rows.
2 rows. 3 columns. Row goes across, columns go up and down. Just like columns on the Roman architecture. Right? Now, how the hell? So that's 2 times 3. There's no question. That is 2 times 3, and we can see it's 6, so everything looks good. Yay. How am I going to throw on top of that times 4?
Would you just draw it 4 times? That particular.
I could draw it 4 times, but I could also kind of like stack them. So I could draw that same image 4 times, and that would be acceptable. But watch, look what else I can do. That's what I said about your artistic ability.
Jeez.
You ready?
I did circles, man. I did circles, man.
Huh?
Yes, circles.
That's not good. I told you not to. Now listen. How long is this supposed to be? How many elements is this supposed to have? 4. This is 2. This is 3. Now I'm doing 4. So I'm going to have 1, 2, 3, 4 pieces. You see that? And if you're an artist or something,
You're
you
asking
well.
about our artistic ability, jeez.
No, I'm not judging. Holy shit. I'm sorry if it came off that way. I have, it's not 0 artistic ability. It's really close.
But you would take the drawing the
Oh my God.
tray 4 times, right?
Oh, yes.
Yeah, I can't.
That's the 2D version of this.
But, real quick, yeah. How would,
I'm trying to see it like not in a cube, like.
I know.
so another
Like,
way
see
to
it
do
as
it
a
is to
black.
take 2 times 3 and just draw that 4 times. And what I would need you to understand is when I drew it like this, I'm actually taking these and stacking them next to each other. Do you see that?
Yeah, right behind each other.
Yes.
Sure.
And the nice thing about this is, you remember the formula for area is length times width, yes? What's the formula for volume? Length times width times height. So if I have a 3D thing, length times width times height, it actually matches with the geometric idea. Do you guys see what I'm saying? So you're kind of like having a little preview of geometry at the same time, right? Without talking about it, okay, maybe. So there are reasons you'd want to draw something like this. There are reasons that you should learn how to draw better than me. So what would be different here? What was the first thing I drew over there?
The front face.
Front face, with 2 times 3. Now I'm not saying you have to draw like some sideways shit. How am I gonna, what's the first thing I'm gonna represent here?
3 times 4.
Yeah.
So you would use like kind of parentheses first, like the whole PEMDAS thing?
Yeah.
Good old PEMDAS, yeah. Always saves our ass.
So my question is, when you drew it below that, like, brick thing that you drew, how come you only drew 3? Why wouldn't you draw 4?
Oh, I get tired, I'm sorry.
Okay.
I mean, well, I did enough just to show that's the end. Okay, that's my fault. You're right. So here I would make how many rows? 3. How many columns? 4. So this is 3 times 4. And then you could either just do that twice, or you could throw in the 3rd dimension in the back. Wrap this around. See that? Now, I mean, and then of course there's 2 of these, right? So I want to do this. There's 2 of them now. Wrap it around. And the really sad thing for me is, this is pretty good. So, I'm trying not to cry from all your critiques. No, you're right.
But
Yeah.
on the test, either of those would be right.
No, careful.
Wait, wait.
What do you mean either of those? What
I
do you
like,
mean?
like the 3D version and the 2D one.
Yeah, sort of.
Like you could do either one and it would be right.
Sort of. Yeah, it should be this really, but I was trying to be nice with them. Okay. Now, real quick, can you imagine picking this up and holding it? Right. And we have those cubes in there. It's not really different lengths and so forth, but you can imagine picking this up and holding it. Could you pick that up, hold it, and turn it so it becomes this guy? Do you guys see that? So then, doesn't that show? It's a nice geometric proof that these 2 things are equal. It shows the associative property seems to hold, at least for these things. Yeah. Is that all right? Maybe? Okay. So the important thing there was rectangular array method. It could either be using set model, which is where you just draw so many little things, but you do it in like an array. Or, I don't know if anyone understands the ice cube model. So this looks like an ice cube tray, right? Yeah. That's the measurement model for rectangular array method. Okay. All right. Yeah. So with addition, we talked about all these properties, right? So we're going to do the same thing with multiplication. Multiplication is going to have one extra one. And it's not because it's special, it's because it actually is how it reacts with addition. So what's the most common, the basic one is commutative. And we already kind of touched on that. So if I did 2 times 3 versus 3 times 2, it would just be flipping this, flipping that over, right? So if I just flip it over, I can see physically they are the same thing. Guess with me. So it's a nice geometric, concrete example that commutative property holds. Okay. Then the associative one we just did. And then, let me not miss anybody. Yeah. The next one would be, oh, I lost the main one. Let me put 0 up here. Closure. What did closure mean again? Besides what you're trying to get?
It'll be all real, no, all whole numbers.
When you operate with the operation on 2 elements of a set, your answer is in that same set. So let me say that a little less mathy. In this case, when I multiply 2 whole numbers, the answer is a whole number. That's closure. If I multiplied two whole numbers and I got a decimal, that's not closure because I didn't stay in the set I started in. Does that make sense? That's what closure is. If I start with whole numbers and I operate and I still have a whole number, that is closed, right? So
You should always have that, right? Like,
no, again, it's based on the operation. So what if I use division? We already did
Divided
this.
by two.
If you take two whole numbers and divide them,
Yeah,
do
you're
you
not-
get a whole number answer? No, you get fractions sometimes,
So-
right? So you could do 8 divided by 4 and say 2 and you go, that's good, Jeff. No, 8 divided by 3 is holy shit. It's not in my whole numbers, it's outside. That's why I love the idea of closure. It's not a
And that
bad
would be
name.
considered not closure.
That would be not closed. So whole numbers are not closed under division. But whole numbers are closed under multiplication. Because you cannot tell me any two whole numbers that you multiply and you don't get a whole number answer. You cannot. And if you think you can, tell me. I want to see that shit. Right? Okay. Now we get the new one. I'm sorry, not yet. Identity. What's the multiplicative identity? What do I multiply by to maintain a number's identity? So I don't change it. What do I multiply by and it doesn't change?
One.
No, 0 would change everything to
One,
0.
not one.
1, really. So the multiplicative identity is 1. Sweet. Now it's the new one. Distributive property, right? Now this gets interesting. Distributive property is not just related to multiplication. We can identify two sub-classifications. Distributive across addition and distributive across subtraction. As a math teacher, those are the same to me because addition is subtraction, just adding the inverse. But I can distribute across addition, I can distribute across subtraction. For your sake, do you know why that works? Just talking to you on our mathematical level for a minute. Do you know why I can distribute that? First off, why must I do something different? Because what would order operations say to do first? Second? PEMDAS. Well, what does it say I have to do first? Parentheses. What's x plus 2? Oh, exactly. X plus 2. I don't know what the shit is. So we need a way, not really around PEMDAS, because you cannot break that, but I can reorganize the problem. Because remind me, what does 4x mean?
there are
For
four
something.
X's.
4x is doing what? No, that would be x to the fourth.
It's just
4x is 4x's adding. So what do I have 4 of?
X.
Oh,
X plus
I have
two.
4 x plus 2's. So if I rewrite it, yeah.
Why wouldn't you just distribute the 4?
that
Okay,
is-
real quick.
That is.
No, stop. I love it. We're proving that works. Yeah. And again, that is, and please, dear God, that was a beautiful question. I would hope somebody would ask the damn question like, I get this all the time. Why the shit are you making this so hard? I'm proving something right now. And you can see this is exactly the parents' misunderstanding. They're like, well, they just tell a kid to distribute. Why does it work? Maybe it's not important to you that your student understands why it works, but it's important to me as a teacher, right? Does it make sense? And I didn't mean that towards you. Okay.
No.
So now what can I do? Become a 2.
Add the twos, so you
Add the
probably.
And actually, just to make it really formal for a second, you're about to use 2 properties. Aren't there parentheses?
Yes.
Aren't you going to shift what's inside of them? Isn't that what property? Ass, that's right. Associative property. That's the associative property. And what else are you going to do? Aren't you going to move individual things around? Commutative, I love it. Using ass in common. So, you end up getting how many x's?
4.
That's crazy. And how many 2's? 2, 4, 6, 8. So the shortcut, distributive property, is a shortcut. That is what it is. Right? There's no reason it should necessarily work. it feels like we're going against order operations, which your teacher will be like, you cannot go against it. So we didn't go against it, we reorganized it. We made everything addition because that's what frickin' multiplication means. And then I can add whatever the hell order I want to. So now that's the shortcut, don't do that. Now, how are you gonna show your students this? Because you're not gonna throw X's at them when they're 7 or something.
No, we're making the next Einsteins.
No, I wish we would, to be honest. I wish we would introduce some algebra notation in early, but you can maybe do that.
Yeah, they're pushing
So this is kind of neat. So if I want to do 2 times 3 plus 4, now of course I know you all know the answer, so that's not the purpose. How would I illustrate this using some of the visual methods we've done? We don't have to use a cube because I'm only multiplying once, so it's really only 2 dimensions.
make a little box.
How would I represent that?
3 plus 4.
3 plus 4.
3 dots, 4 dots.
Yeah, so let me kind of move us, well actually, sure, what the hell? 1, 2, 3 dots, and then I would put 1, 2, 3, 4 more dots. I love it, right? And then what does that tell me to do?
Do it again.
Do it again, right? I want 2 of these groups of things, right? So then I would just repeat.
And that's the answer.
And of course, you can have a student count that and they'll get
The answer.
14, right? Now, real quick, just to point out how this relates to distribution. What is this?
6.
That's 3 times 2, yes? So it's 2 times 3. Plus, what's this? 2 times 4. 2 groups of 4 things, right? Are you guys at all with me?
Yeah.
Didn't we just distribute the 2? And you can see
Do
it.
you want us to draw like that?
Say again?
Do you want us to draw?
The way I was gonna draw, but I'm cool with the dots. I was gonna draw 2, 3, 3 of these and then 4 more. So it's probably better to get dots. And then you just do it twice, right? It captures the exact same idea, because then this would be the 2 times 3 and this would be the 2 times 4. You see that?
Can we go dots though, or square?
Yeah, sure.
Yeah.
You can go dots. You can go dots. I like that. It's a new phrase. Go dots. Feel free. Go dots. It's a weird team name. Go dots. You guys, yes.
I need to ask a stupid question.
Anytime.
So I guess it's me knowing like how to do it right away. Like, why wouldn't you just, or how would you explain that you're not just adding the stuff inside the parentheses and then multiplying it outside, rather than distributing?
So this is a really early example where we can show them distributive property.
Mhm.
Now, I would hope I'd have a student that would say, teacher, we know what 3 plus 4 is. And then I would go, cool, what is 3 plus 4? And then they would say, 7. I'd say, okay, what's 2 times 7? 14. I go, oh, did you get the same answer we got this way? Yeah. So it's students, especially if you get young enough, they are just sponges and they will take anything.
Yeah.
They're just ready. And of course, they get to a certain age and then they become like, you guys all know this, right? We've all lived through that time, right? Hopefully we're all out of it. But this is an illustration of an idea. You can tell them later when you get higher up in mathematics, this is gonna have a very important use. And then we just wanna show concretely that it actually works, right? You guys kind of, okay. And this is a nice illustration of accepting what a student's saying and saying, oh, let's see what we get if we go your way. How about you get the same thing we got? Okay. Are you guys semi with me? So of course, if this was a problem on a test, I would hope students would do 3 plus 4 because that's showing they know order operations. But if the instruction said, use distributive property on this, I would tell my students, you can check your work doing it this way, right? Okay. And that's, as a math teacher, very often I have to say, I want you guys to do this a certain way because it will help us later. And somebody says, but I can do it this way. I'm like, that way will not help us later. You could do it that way, but I need you to understand this way because it will help us later. Do you understand what I'm saying? So that's an example of still being flexible, but trying to push students in a way that you know will help them later, right? Okay. Oh, and then this came up earlier somehow, I can't remember how. There's a whole property for this. The property is multiplication by 0. And what is that property?
Something in 0 groups, how many groups?
0 times anything is 0. That's amazing. Okay.
But then anything to the property of 0 is 1.
To the power of 0. Yes. Yes. Cool. And that's going to come up a little bit later. We have exponents in our
But I
future.
thought anything times 0 was 0, and 0 times 0 would be 1.
What do you mean 0 times 0 is 1?
Because that's like, well, 0 to the power of 0.
0 to the power of 0.
Is 1.
No.
Is 0.
Very quickly. You ready? What's 0 squared? 0 cubed?
0.
What's anything to the 0 power? Except 0. 1. So somehow this is both 0 and 1 at the same time. Don't freak out. This is so weird, we don't even call it undefined. We call it indeterminate.
But we don't need to know that
Cannot be determined. It's worse than undefined. Alright. So
At least
that's not
defined
gonna
has
come
a
up again, okay?
definition.
Huh?
At least defined has a definition. Like undefined.
Yeah, undefined has a definition. It's a number we haven't defined. Yeah. That's not even like what? Alright. Okay. Yes, let's do this. Alright. I just want to point out very quickly. You have multiplication tables, right? And we could talk about the same thing we did before with addition tables. The easiest rows to fill in would be which ones?
0.
Yeah, the 0 rows. 0, 0. The next easiest would be
1.
the 1s. The next easiest would be the 2s, because 2 multiplied by 2 just means double, right? Okay. Now after that, you can start using different strategies like the commutative property, the associative property. So again, commutative property says I only have to know like half of this. If I know this, I know that just by turning them around, right? You guys got it with me? So you can do something very similar with what we did with the addition table before in terms of how to fill it all in.
This one's the multiplication.
Multiplication table. Okay. Was there anything interesting there? Not really. No. Real quick, this book does something. We're going to learn this later, but I just want to do a little preview because the book sort of does a little preview. What do you get? What's special about things when I multiply them by 9? Does anyone know?
You can go with this.
They're kind of inverse if you line them up.
Oh yeah, sure. What's 9 times 8?
72.
72. What's 7 plus 2?
9.
What's 9 times 5?
40. Wait.
We're at 54.
45.
45. What's 4 plus 5?
Yeah.
9.
So any number where the digits add up to be a multiple of 9, it can be divided by 9. So for example, this number here, be very careful. I don't know if you guys noticed. There, okay, that should work. Does that work? What does this add up to be? 9, 11, 18, 21, 27, 28, 29, 30, 31, 36. Is that a multiple of 9?
Yeah.
Yes. So if I, does somebody have the calculator or something? What is this number divided by 9? Can anyone do that very quickly? Anybody? Do it in your head. Do it in your head. No, I'm joking. That'll be 50304. I'm sorry. I
You
get
said
lost.
divided by 5?
Divided by 9.
It's a long number.
9. But it's a whole number, right? There's no decimal to it. Yeah. So it's like 5.
5, 0, 3, 0, 4, 0, 1, 6, 7, 9.
Okay, cool. All right. Yes.
But would that work for any number?
No.
No.
Hell no.
Just not.
Hell no. Right? Does 4 go into 16?
Yeah.
What's 1 plus 6?
Oh, 7. Okay.
So it's
Thank you.
only 9 and 3. And of course that kind of makes sense because 3 goes into 9. If I take any number and all the digits add up to a multiple of 3, 3 goes into it.
Doesn't 6 work too?
6 would be any number that is both even, because 2 goes into 6, and where the digits add up to be a multiple of 3. Now, I'm sorry, this is all a preview. Later, we're going to talk about all the numbers. Have any of you ever heard any of these before? I know some of you guys have heard 9.
I know 11 has a weird one.
11 has a very weird one, but it does have one. 7 has a very weird one. Very weird one. Yes.
I just found a weird one. Dude, the 9 ones divided by 9 is 1, 2, 3, 4, 5, 6, 7, 8, 9.
Say again?
9 ones divided by 9 is 1 through 9.
Yes, cool. I love it. Sorry. A lot of nifty little shit. There's a lot of it. Alright, sorry. It's a preview. Okay. There are rules for most of the numbers, and that's kind of nice. Now, part of me always said, when I tell students this and they never heard of it, I'm like, you really should be angry if you think you've never been told this.
Yeah.
Because we created the numbers. We're humans. We should be told how the shit they work, right? I know we have calculators, but still, I'd love to know if 9 goes into a number. I'd love to know how to tell that. I'm a freaking human. I should know some shit. Okay. Sorry, when I'm walking here, just move some shit. Now, a little bit about division, and then I'm going to let us out a little early. Remind me, the basic idea of multiplication was what?
Addition.
Repeated addition. So what do you think the basic idea of division should be? Repeated subtraction. Let's see what the shit that means. You ready? So if I want to do 15 divided by 3, I know you all know the answer. It's amazing. What happens if I repeatedly subtract 3? Let's see what we get. You ready? Start with 15. Subtract 3. What do you get? Oh, holy shit. Subtract 3.
9.
Subtract 3. 6. Subtract 3. 3. Subtract 3. 0. How many times did we subtract 3? 1, 2, 3, 4, 5. 15 divided by 3 is? 5. Now, this is not surprising. Now, to some of you guys, it might be like, whoa, because you've probably never seen that shit before. And you all know multiplication is repeated addition, so of course freaking division is repeated subtraction. Of course it is. Are you guys kind of with me? Now, real quick, what's wrong with this then, in a way? 16, let's do 17 divided by 6. What's gonna be a little freaky with this one? Yeah, so let's try it. 17 minus 6.
11.
11 minus 6.
5.
5. And then I can't subtract 6 anymore, right? Because for us currently, no negative numbers don't exist. How many 6s? How many times did I subtract? 2 times. How much did I have left over? I had 5 left over 6, so 2 and 5. Oh, that's a little bit of a fraction. Or let's do it this way. 2 big S R 5. Is that better? Okay. You guys kind of with me? We'll do the big S R for now. Fractions are coming. I feel like this is a weird Game of Thrones.
Yeah.
Fractions are fractions. And then when they get here, it's like over. What the shit was that? Sorry. I'm still a little upset about season 7 and 8. All right.
What's that about season 1?
Huh?
I'm still mad they killed my man Ned Stark.
Oh, very true.
That one hurt.
But that,
I haven't even seen
very
the show. Is it
strangely, I
good?
love shows that do that. Have some balls. Do something like that.
Yeah,
I
but
love
That's
it.
how you know it's gonna be good.
Him
And they lost all their
him and
balls
the
when it
king
came to
in the
season
same
7.
line.
Sorry.
Him and the king in the same season? Sorry.
I'm sorry. That was my fault. Okay. So repeated subtraction the same way. And the really cool thing is the remainders come out. Now, very obviously, we don't want to do this for everything because I don't want to do 8,437 divided by 4 that way. Correct?
Why not?
You could. In fact, I want you to.
No, thank
I
you.
expect it.
Do I get extra credit?
Do it.
Extra homework.
Then what's the point?
The point is, if you don't do it, I take points off.
Oh, man.
Now, obviously, what was the next thing we said about multiplication? I wanted to tie it into stuff they've done before, so you could do the missing factor method, right? In fact, did I even? Please tell me I did that. I feel like I didn't even talk about that. I think I did. I might not have. I didn't even write it down. So very quickly, backtracking a little bit. When I have multiplication, and I want to do, no, I'm sorry. I'm talking about division. I'm good. Division. if I do a missing factor approach, sort of like with subtraction, I could do a missing addend approach, right? So if I wanted to do 16 divided by 8 equals what, this must mean 8 times what equals 16. Exactly the same way as the missing addend approach. Are you guys kind of with me? And again, why would this be a good method to show for somebody? Because it builds off of what they would have just done before they did division. They would have done multiplication. So they know their multiplication tables, or at least they've started to get them in their head. So then this kind of question becomes much easier if they realize that's how to reformulate it in your head. In fact, a really good example for you guys, I already did this earlier with people, is when I put that down, what do you think?
Square root.
What do you think, though, to get the answer? What do you actually do in your head to get the answer?
See what numbers will the same two numbers.
You do the opposite of what this is asking, right? You kind of think back, you say to yourself, what does this symbol want from me? It wants, what does it take 2 of to multiply by 49? So this is really just showing them, what does this symbol want from me? How many of these make that when I add them? That's really what that's asking. So that's why the answer is 2. Now, real quick. 16 divided by 8 is 2 because 8 times 2 is 16, correct? Okay, what is 6 divided by 0? What would it have to be? 2 is the number that when I multiply it by 8, I get 16. That is why 16 divided by 8 is 2. What would 6 divided by 0 have to be? It would have to be the number that when I multiply it by 0, why is this 2? 2 times 8 is 16. Whatever number this is, it better be the number where when I multiply by 0, I get 6. Do you guys see that? Why does this work? Isn't 2 times 8 16? What is 10 divided by 5? Holy shit, because 2 times 5 is 10, yes? 2 is the number defined in such a way that when I multiply by 5, I get 10. So this would have to be the number defined in such a way that when I multiply by 0, I get 6. What do I get whenever I multiply anything by 0? So do we have a number defined in such a way that when I multiply by 0, I get 6? That's why the shit we call this undefined, right? You guys with me? Y'all, I'm pretty sure y'all know this is called undefined. Some of you guys might have called this infinite. I don't know. Most people call it undefined. That's why. Because there's no number defined to do what this guy wants me to do. Maybe. Okay. I think that's plenty. That's enough for today. So next time, I'll go a little bit further. We'll have a bit of a handout. I'll have some manipulative stuff. We'll watch some more videos maybe. We'll see how much time we got. Videos are always good. Okay.
Yeah, we wanna see that silly one.
Yeah.
Oh, yeah.
Silly one, and you
But
can
let's,
show us the
no, let's
silly
start the
one.
video right now.
Yeah, you can, if anyone wants to see, you can see it.
All right. If you want to see it, obviously I won't record, but